This is a paper presentation of CS643 Cloud Computing, presented by Group 3. My name is Bicheng Xiao, and my colleague is Hivarekar, Pranav. The paper we are talking about is Virtualized Congestion Control. Here is the authors of this paper. They are from Stanford University, VMware, and Techland in Israel. We have many 6 parts, and I will present the first 3 parts, and my colleague Mr. Pranav will do the rest. Let's look at the first part, the introduction about the background of this paper. First of all, let's see some keywords that were used in this paper. VCC, Virtualized Congestion Control, Algorithmic Virtualization, and Data Centers, and Hypervisor. Hypervisor or virtual machine monitor is computer software, firmware, or hardware that creates and runs virtual machines. ECN, Explicit Congestion Notification. ECN allows end-to-end notification of network congestion without dropping packets. ECN is an optional feature that may be used between two ECN-enabled endpoints when the underlying network infrastructure also supports it. DCTCP, which means Data Center TCP, Data Center Transmission Control Protocol, utilize ECN to enhance the transmission control protocol congestion control algorithm. It is used in data center networks. And TCP. Congestion control algorithm is updated and advanced day by day. It is important for the reliability of the internet, especially for data centers. However, some old servers in data centers cannot upgrade to a new operating system, which also means such servers cannot be applied with latest congestion control algorithm. While the old servers sitting in the same data centers with the new servers, they will face serious starvation. The proposed solution by the authors is to use hypervisor to translate between the new congestion algorithm and the old congestion algorithm, allowing the old server and the legacy applications can enjoy the benefits of the new algorithm. We can call it VCC, Virtualized Congestion Control. Here we can see the VCC translation layer is sitting in the hypervisor, while it translates the guest's legacy congestion control to a target congestion control algorithm. In other words, the guest congestion control algorithm is an overlay algorithm, while the hypervisor translates it transparently to the underlay algorithm used in the data center network. The hypervisor will do the translation between the new congestion control algorithm and the old congestion control algorithm. Here we can see it's a starvation of legacy application case. In this figure, the figure shows 10 floors share the same bottleneck link. There are 1 non-ECN floor from a legacy application, 8 ECN-enabled floors, and 1 non-ECN floor augmented by virtual congestion control translation. From the figure, we can see that the non-ECN floor is starved, reaching only 10% of the ECN output on average. But after translation to virtual ECN, the average output is near identical to that of the ECN floors. Here's another concept of algorithmic virtualization. Algorithmic virtualization is about implementing a common algorithm while making each guest believe that it keeps using its private algorithm. The hypervisor implements a common best-of-breed congestion control algorithm while allowing each guest to keep using its private legacy congestion control algorithm. We can check this formula. X is an input sequence. F is the data center congestion control algorithm. So the Fx is the target output we required. And G is the private guest overlay congestion control algorithm. The goal of our hypervisor translation layer T is to map input X into Tx. Then we can get our target output by applying Tx to algorithm G. The second part, we will introduce the hypervisor translation techniques. In this section, I will introduce 8 hypervisor translation techniques may use in the solution. All these techniques would affect the network. We will check them one by one. First, writing to guest memory. Hypervisor could directly modify the congestion control algorithm in the guest by writing the desired TCP parameters in the corresponding guest memory and the registers. There are two main disadvantages of the techniques. First, tenants may not accept that the hypervisor writes into the virtual machine's memory. Second, keeping consistency and ensuring centralization between the write operation would slow down the virtual machine. Second techniques, read from the guest memory. In order to avoiding memory writes, hypervisor only monitors the memory and does not need synchronization. Similarly, tenants may not accept that the hypervisor gets a sneak peek inside their virtual machines, and accessing the guest memory instead would add processing and communication delays. The third technique is the split collection approach. This approach breaks a TCP collection into several sub-collections. For example, using a TCP proxy, it can acknowledge packets to the guest virtual machines at some desired rate, then send them on the data center network using the desired target congestion control algorithm. This black box solution function is working as a pipe and can implement nearly any congestion control algorithm. However, in addition to requiring many resources for buffering packets, this solution goes against TCP end-to-end semantics. For example, a barrier-based application may believe that all its packets were acknowledged and advance to the next phase, while they were not actually received. This situation will potentially cause errors in the application. The fourth technique, buffer packets. The hypervisor translation layer can buffer in-flight packets, for example, to be able to resend them without informing the guest. Nevertheless, the hypervisor needs to manage package buffers. Package buffers may also increase latency when they are used to store packets coming in too quickly. Large buffers significantly increase the memory footprint of VCC. The fifth is buffer X. The hypervisor can similarly buffer received X if an X is piggybacked on data, the acknowledged sequence number is reduced and the remaining bytes of acknowledge are later sent as a pure ACK. Same as buffer packets, it may also increase latency when acts are delayed. The 6 duplicate acts. The hypervisor can duplicate and resend the last sent act to force the guest to half its congestion window, but this technique may also violate TCP semantics. For example, sending 3x on the last outstanding packets means that 3 additional packets have been received, which cannot happen. The 7th, throttling the receive window. The hypervisor can decrease the receive window to force the guest to have fewer outstanding packets. Since the number of packets in flight is upper bounded by the minimum of the congestion and the receive window, therefore, the advertised receive window could follow the target congestion window to make the guest adapt to this target. This technique can make the congestion window meaningless, since it relies on the receive window to bound the number of in-flight packets. Also, a delicate point to note is that the receive window should not be decreased to less than the current number of in-flight packets. This may conflict with common implementation of the TCP buffer management. So, the hypervisor needs to manage a gradual decrease while closely monitoring the collection states. The 8th technique is modifying the three-way handshakes. The hypervisor can change the options that are negotiated when setting up the collection. However, this technique must rely on other additional techniques. Let's check a combined techniques case. The figure on the left illustrates how a combination of three-way handshake modification and receive window throttling techniques can help provide virtual ECN benefits to non-ECN TCP traffic. The VCC translation layer in the hypervisor first uses the three-way handshake modification technique, which means in the part A of the figure. It modifies the TCP header fields of the sent packets to enable ECP support in the underlay. Next, while the VCC only sets the ECT bits in the IP head of outgoing data packets and forward incoming X transparently. We can look at the part B of the figure. It uses the receive window throttling techniques upon the congestion. As shown in part C of the figure, upon receiving an ECN congestion notification, it decreases the advertised receive window to force the guest sender to reduce its pace and behave as if it were ECN aware. It also modified the TCP header fields of the ACK packets to mask congestion notification in the overlay. Evaluation 1. In this section, we will see some experiments which evaluate the starvation of the proposed solution. Experiment A. We use 10 floors going through a shared 100 Mbps bottleneck link, and the figure is a result of the experiment. This figure demonstrates the unfairness between ECN and non-ECN floors by plotting the time series of their output. It shows that while the ECN floor fairly share the bottom link among themselves, the non-ECN floors can become significantly starved. The unfairness grows as ECN become more widespread and the ratio of ECN floors to non-ECN floors increases. As applications increasingly adopt ECN, the holdouts legacy applications became increasingly stuffed. Limited unfairness between ECN and non-ECN TCP floors was known given equal numbers of floors in each group. Experiment B is similar as experiment A. We use 10 floors going through a shared 1 gigabps bottleneck link, and the figure is the result of the experiments. The experiments with higher rate links is more close to a data center environment. The result shows the same trend that the unfairness grows as ECM becomes more widespread and the ratio of ECM floors to non-ECM floors increases. Experiment C, we put different ratio of ECM to non-ECM floors and various RED parameter sets, which lists on the right of the slides. All floors are running through a 10 megabps link and a 100 megabps link. The figure shows the result. This experiment illustrates how for all tested parameter sets, introducing even a small number of ECM floors into the mixture breaks fairness between ECM and non-ECM floors. Moreover, when there is only one non-ECM floor left out of the 10 floors, its throughput is at almost 45% of the throughput of the ECM floors. In experiment D, we put different ratio of ECN and non-ECN floors and various of RED minimum parameter sets. All floors are running through a 10 megabps link and 100 megabps link. The figure explores how modifying the RED minimum parameters in the RED1 parameter sets affects fairness. The figure depicts the throughput ratio for different values of RED minimum. In general, we see that as the proportion of ECM floors in the mix increased and as RED minimum decreased, the unfairness worsened and the line ECM floors suffer from increasing throughput loss. In order to address these unfairness problems, we propose using the VCC translation layer to provide ECN capability to the non-ECN floors. We transform non-ECN floors from a guest to virtual ECN floors that take advantage of ECN. Using receive window throttling in the VCC translation layer. This figure depicts the send window for the VCC experiments as reported by the TCP probe kernel model. We can observe the familiar sawtooth pattern that would otherwise be seen in the congestion window. In our Linux implementation, when the receive window was the limiting window, the congestion window stayed larger than the receive window for the entire experiment, rendering the congestion window meaningless. So, modulating the receive window would also modulate the send window of the guest directly, and the resulting traffic flows are very similar. We have therefore created a virtual ECM floor. To demonstrate that indeed we get an ECM benefit of the reduced retransmission when using virtual ECN, we run an experiment with 10 identical senders collected with 10 megabps links to a single receiver through a single switch. The figure illustrates that when using only non-ECM floors, some 2.3% of the link capacity is wasted on retransmission due to the packets dropped in the congestion queue as a port collecting the switch to the receiver. However, as shown in the part C, once virtual ECN is activated, the lost capacity is regained as virtual ECN can reach can react to congestion without dropping packets and retransmitting them. It shows again how the line ECN suffer from strong unfairness. This is an experiment of restoring fairness with virtual ECN. 9 ECN floors share a 10 megabps bottleneck with one non-ECN floors or one virtual ECN floors. VCC offers the ability to transform a non-ECN floor into a virtual ECN floor. We now evaluate whether this is sufficient to address the unfairness discussed in previous experiments. Part A shows the throughput achieved with 9 ECM floors and one non-ECM floors sharing a 10 megabps bottom link. And Part B shows the throughput achieved in the same setting except that the non-ECM floors has been replaced with a virtual ECN. The resulting throughput of the floor from the ECN incapable gas is now similar to that of its ECN capable peers, with throughput 103.8% of the average throughput of the ECN capable floors. To summarize, the translation layer using receive window throttling to cause the guest that does not support ECN to mimic its ECN peers, significantly improving its own throughput and the fairness of the network. That's all of the first three parts, and my colleague Mr. Pranav will present the coming slides. Thank you.
Here we talk about how researchers evaluated against bandwidth sharing. Researchers described the proof of concept VCC translation layer which they implemented on the VMware vSphere hypervisor, and later they showed how it can be used to provide bandwidth sharing. Now let's get started. Hypervisor bandwidth sharing. Here we are going to talk about DV filter, limitations and other approaches to bandwidth limiting, and the application of receive window throttling abilities of VCC. Let's start with DV filter. The VCC translation layer is implemented as a filter called DV filter in the hypervisor switch. The translation layer monitors flow passing through the switch and inspects the headers in order to maintain correct state information about the flow. It can edit the information on the fly if needed and passes through the filter. This is what the DV filter does. Now we'll take a look at the limitations and other approaches we can use for bandwidth limiting. We want to implement bandwidth limiting application wise for a multi-tenant data center. If we go with WAN traffic shaping, which allows you to dynamically allocate bandwidth to individual applications, but it requires a uniform OS installation that does not allow multi-tenant hosting, so we cannot use it. Now if we consider modern hypervisors like Microsoft Hyper-V, these provide bandwidth limiting per application. Here we have bandwidth limiting is available, but per application throttling is not available. If it's available with them, then it will completely rely on dropping packets or building large queues, which will impact performance. Now let's talk about another application of receive window throttling abilities of VCC. By controlling the end-to-end number of in-flight packets, VCC provides a fine-grained data center-wide coordination of bandwidth allocation. How it works is that the hypervisor detects the signature of a tenant port or packet and restricts the bandwidth used by a particular set of traffic. In addition, bandwidth limit can be changed dynamically depending on signals from the network or from the guest. Now let's move on to next slide. Now Here, researchers did an experiment. Here, researchers showed hypervisor implementation for dynamic application granularity bandwidth throttling. Here, they are running two guest VMs hosted on top of hypervisor with VCC translation layer installed in its vSwitch. VMs communicate through that hypervisor vSwitch. They divided flows into preferred and unpreferred flows. Now, in this figure, a time series of this experiment is shown. It shows that after introduction of preferred flows, the throughput of unpreferred flows drops due to receive window throttling, thus providing the preferred flows a larger share of bandwidth. The total throughput before and after the introduction of preferred flows remains relatively constant. Now you can see in this figure. Now this is how it was evaluated. Now let's move on to next slide. Here we'll talk about implementation. Let's look at architectural issues that a VCC implementation needs to address in the hypervisor. Now there are total 11 issues given in the paper. Let's try to check it one by one. First one is architectural complexity. Many hypervisor switches support an architecture where an independent module can inspect, modify, and re-inject the packet. This architecture is used by firewalls and security modules. A VCC implementation can leverage this architecture in order to modify packets. For example, Linux VCC implementation stores only 37 bytes per flow. This leaves room for a more complex implementation given a per connection footprint budget under 1 KB. Now let's look at second point, that is hypervisor delay. Processing delays in the hypervisor can increase latency, then flow competition time. This affects the algorithm. VCC implementation needs to address this. Now the third one is hypervisor bypass. High performance virtualized workloads can benefit from bypassing the hypervisor and directly accessing the NIC. NIC stands for Network Interface Card. VCC would not work in such architectures. VCC implementation needs to address this via different methods. Now let's talk about the fourth point, that is TSO and LRO. TCP segmentation offload and large receive offload are techniques for increasing the throughput of high bandwidth network connections by reducing CPU overhead. TSO transfers large packet buffers to the NIC and lets it split them, while LRO does the reverse operation. The hypervisor needs to modify the VCC translation layer accordingly. Now let's talk about the configuration. In the VCC architecture, the network administrator can assign a different congestion control to different ports, IP addresses, applications, OSs, or tenants. Now the sixth point is delay-based congestion control. VCC can translate to or from delay-based TCP algorithms like TCP, Vegas, and Timely. Now let's talk about UDP. Now we have seen the idea implemented for TCP. We need to implement the same idea to support UDP. The eighth one is universal language. In order to directly translate between n congestion control algorithms, we would theoretically need to implement ON2 translations. Instead, we could envision a universal atomic congestion control protocol enabling us to implement only 2n translation 2 from this protocol. The ninth one is encryption. VCC architecture can similarly be used to offer encryption services such as TCP crypt and IPsec to legacy encrypted TCP flows. The 10th one is debugging. Adding packet processing modules at the connection endpoint necessarily makes debugging more complex when there are connection issues on a host. On the other hand, normalizing all the control congestion algorithms to the same reference algorithm as enabled by VCC. The last one is inside connection. When two guest VMs on the same supervisor hypervisor communicate, they still go through the hypervisor and therefore through the same translation layer. As a result, VCC is expected to work without changes. These are the 11 points we need to address while implementing the VCC. Now let's move on to the next slide. Now, conclusion. In conclusion, this paper presents VCC, which enables the data center owner to introduce a new congestion control algorithm in the hypervisors. Internally, the hypervisors translate between the new congestion control algorithm and the old legacy congestion control, allowing legacy application to enjoy the benefits of new algorithms. Using the example of ECN traffic, we show how this VCC solution can have an impact on fairness among tenants. Now, the future goal is the hypervisor translation layer will provide hooks that would simplify the coding of new congestion control algorithms similar to the existing hooks in the current Linux TCP stack implementation. These hooks would significantly reduce the deployment time of novel congestion control algorithm in large scale data center. That's it for this presentation. Thank you.